All right, so thank you. So I'm Kelsey. I'm from NIST. I'm also a new PhD student here. And so this is the second talk I'm giving this week. So hopefully I won't completely confuse everybody. So title of the talk, I just wanted to get your attention. So random numbers, entropy sources, and I'm mainly going to be talking about, first of all, about kind of cryptographic random number generation, how it's typically done, kind of what the structure is, sort of some of the assumptions that people use. I'm going to talk about entropy, kind of the intuition for what entropy means and what we use, kind of how we measure it, and the specific choice of min entropy is the measure that we use. And then I'm going to talk about 890B, which is the new document that should be coming out fairly soon, that is a document about how to build an entropy source. So I'll talk about what an entropy source is in our kind of thinking and how it fits together in the big picture of cryptographic random number generation. So hopefully, if you have any questions, I'd love to hear them. So please feel free. So this is just some terminology to start out. An entropy source is the non-deterministic thing. If you think about a big cryptographic system, you kind of want to put all the non-deterministic stuff in one little box, and that little box is the entropy source. That's where you get your unpredictability from. It's non-deterministic, and it's supposed to provide you, in our conception, it provides you a known amount of entropy. So it's not just something that has some unpredictability, it can tell you how much. Okay? The second term is entropy. Roughly, it's kind of a measure of the uncertainty of a number, how hard a number or a bit string is to predict. You can kind of think of it as this k bits of min entropy in particular is like 2 to the k guesses to guess it. Entropy is sort of a more subtle concept than that, and I'm glossing over a little precision there, but that's a good first cut of understanding what I mean. Conditioning is when you process some sort of entropy source or noise source outputs to get to basically improve the statistics. Okay, an entropy source often has conditioning going on. And finally, a DRBG is the term that we wound up with in the 890 series for what everybody else in the world calls a cryptographic PRNG. What you need to think about this, it's deterministic, right? It's an algorithm. It's not, there's no entropy in this. You have to provide it some unpredictable input to start out. It has to be something that an attacker can't guess. And then once you've given it that seed, then it gives you good random numbers. Random bits that can't be distinguished by any attacker within some limits of computation from ideal random bits like somebody who's flipping a coin. So those are 4 ideas, and I'll be talking about them a lot. So hopefully you know at least what my words are now. So what's cryptographic random number generation? The basic problem is you kind of can't do crypto without random numbers, right? You need for generating keys, key pairs, Diffie-Hellman exponents, nonces. Sometimes you can get away with using a counter or a clock, but a lot of times you need random numbers. You need random numbers all the time for crypto. This is not the same sort of requirement you have, obviously, for doing like statistical simulations or something, where you just need them to be, statistically good. You actually need them to be unguessable and unpredictable and indistinguishable from ideal random bits as far as an attacker goes. Okay, it's easy to get this wrong. People do all the time. So our goal, maybe not always met, in the 890 series is to try to help people get random number generation right. Random number generation for cryptography, right? So I'm glossing over a lot of detail here, but there are kind of, in most of the world, you'll see 2 broad models used, especially in software, for generating cryptographic random numbers. One of them is sort of the dev-random approach with an entropy pool. One of them is, you can think of as the Yarrow approach. It's where you have an entropy source just initializing a random number generator, a DRBG, and then that DRBG gives you your bits. And these 2 are somewhat different strategies. There are other ways to do it, like you can have just an entropy source and some conditioning and get ideal random bits out, making some assumptions. But these are the 2 things you see a lot in the world. Okay. So the entropy pool design, like I said, it's like dev-random. The idea is basically you're counting how much entropy you have. So you've got a pool. This is basically some state. Okay, it might be an array of 16 32-bit words. Okay, And then you have an update function that mixes bits, mixes inputs into the state so that you hopefully update that state and spread that unpredictability around in it. Okay, so you get an entropy source gives you some raw samples, some data with some entropy in it, and you know how much you think you're getting. And then you call this update function, and it updates the pool. It mixes this information into the pool, updates that state. And it also updates a counter. It adds, if it thinks it got 10 bits of entropy, it adds 10 to the entropy counter. Okay? And then the other side, and this can be completely disconnected, right, is when there are requests for entropy that come in, you call some output function that does probably hashes the pool, hashes and does some update of the pool. You get those output bits as random outputs, and then you subtract however many bits came out from the entropy counter. Okay? So you're doing two things. So you're updating this state where you're keeping a pool with entropy, and you're also keeping track of how much you got in and how much you got out. And this is the big idea here is just don't allow more to come out than went in. Okay, it's a pretty basic idea, and this is an old idea. This has been floating around for 20-some years. If you look, dev random in Linux is the classic version of this, but I think there have been a lot of other schemes that use some sort of entropy pool-like design. Right. Now, what can go wrong with this? The first thing that can go wrong is blocking. It's the immediate problem that comes up because you don't let me pull more bits of entropy out than have come in. Basically if everybody demands a lot of random bits, then the thing locks up, and you have to wait. And the result is you inevitably, and this is what dev random does with dev urandom, you add a non-blocking version. Then, quite often, everybody uses the non-blocking version, and they don't know whether they're getting enough entropy. So there's kind of an immediate issue there, right? In order to make this usable, there's also something called the iterative guessing attack, which I'm going to talk about in a minute. There are a couple other issues with this. I'll talk about my issues with this more. The other really common thing you see, at least in software sources, or software crypto RNGs, is this sort of idea of an entropy source that is just used to initialize this deterministic thing, this cryptographic PRNG or a DRBG. And then once you've initialized it with enough entropy, then this thing generates as many bits as you want, maybe up to some really high maximum, right? It may require being reseeded after a large number of outputs, but it's a large number. So you kind of get this idea. You initialize the DRBG, you generate a seed which has a lot of entropy in it. Let's say k bit, more than k bits, or k bits is your security level you're shooting for. You might want like k and a half, right? You feed that into the initialization function, and you get this DRBG into a secure state. The requirement here is, if I'm an attacker, you need to be sure that I, as an attacker, have only a negligible chance of successfully guessing that seed, that starting value that went into the DRBG. Then I'm going to generate outputs forever, and then every now and then I may update. So I may wait until I've got enough entropy to reseed again, and then I'll reseed. I'll send in more bits, and I'll update the state of the DRBG in a way that doesn't throw away what it had before, but incorporates new inputs. Okay, and that's the basic idea. The Yarrow 160 is a paper I did, gosh, I don't even want to say how many years ago, probably 15 years ago, but with Bruce Schneier and Niels Ferguson. And it was this is the basic design. We actually had two pools and did something a little bit more complicated. But this kind of design is actually very common in the world. The old X9.17 ANSI standard for banking in the US, key generation kind of, sort of, if you squint, sort of fits this model. The current Intel RNG fits this model, where they're generating some outputs from effectively their entropy source, and then they're using that to initialize and reseed something called counter DRBG, which is a DRBG based on AES. So what can go wrong with this? The big things that can go wrong, obviously if you initialize it too little entropy, then you've got a terrible problem. And this is a general problem when you're doing crypto RNGs, and actually, especially on computers. This is the problem that comes up all the time. You have some new machine, just fresh from the factory, you turn it on, the first thing it has to do is generate keys. And maybe it hasn't had enough time to accumulate any unpredictability. So maybe you've only got like 32 bits of entropy in there, but the first thing it wants to do is generate a key pair. maybe generate its RSA key pair. And of course, then the problem you have is, even if you recover later, you've still got your key pair that you're using for everything that's easily broken. So initializing with too little entropy is really deadly here. There's also this thing called the iterative guessing attack that I'm going to talk about in a second. The biggest issue is if the DRBG is broken, all is lost. Okay? So if you look at this, let me go back to this picture here. Up here, there's a lot of tolerance because you're always putting a lot of entropy in. If you've got a huge amount of entropy in this pool, every time you put some outputs out, you're not making quite so many demands on this output function, right? You don't have to think this is so great. Whereas with the DRBG, you're just initializing it and generating as many bits as you want. You've got this issue that if you can't build good DRBGs, you're kind of in a bad place, because if this DRBG is broken, everything's just gone. Your security just dies. So let me hop back here. So the next issue that comes up is the iterative guessing attack. This applies to everything. It applies to pool designs as well. The iterative guessing attack, Dotis et al. Wrote this paper which treated random number generators in a very theoretical way, and he called this the premature next attack. I wrote a paper a long time ago with Bruce Schneier and Chris Hall and David Wagner, I believe. It was cryptanalysis of a bunch of RNGs, cryptographic RNGs, and we called it the iterative guessing attack. So, big idea, you have a known state, you update maybe with 64 bits of entropy. All right, great. So now you're getting closer to being secure, but you're not quite secure yet. But then, before you've had a chance to update again, you output 64 bits. Well, once you've done that, then of course, I can just guess all to the 64 possibilities for that entropy that went in before, and I can learn that state because you've given me enough to check my guesses, right? So I basically can say, I'll try for each possible input that could have come in, all 264 of them, I will try guessing that value and seeing if that value would have given me the output that I saw. One of those will give me the right value, presumably, and then I will know your state again. And then you can keep doing this. You can just keep on going, saying, I've put 64 bits in, I've put a 64-bit output out, taken 64 bits of entropy more in, put another 64 bits out, and I, as an attacker, can just stay with you. So eventually you put in thousands of bits of entropy, but you never got to a secure state because you output too soon. So it's a very basic attack that happens for any kind of cryptographic RNG. So with the entropy pool design, imagine your entropy estimate is just a little bit high, okay? Maybe even just exactly spot on, right? You're outputting 64 bits. Maybe you really think you're feeding it 80 bits, and so you let somebody generate 80 bits if they wanted, and you're putting 64 bits in at a time of entropy. So 2 to the 64 possible values. You can think of it that way, right? What's going to happen is you're going to get, you have this. This is a perfect setup for this iterative guessing attack. So you keep thinking you're putting in a lot of entropy. You're putting in a little less than you think you are. You're letting a little too much output come out, and so I get to check my guesses every time you update your entropy, right? So this is a problem that is actually a pretty serious issue with this kind of pool design, right? If I start knowing the state, I keep requesting bits, I keep guessing, you're only getting a little entropy at a time, and I keep guessing it and then checking, you might never recover, you might never get to a secure state. So with the DRBG, entropy source plus DRBG structure, the thing where you're just seeding the DRBG once, and then reseeding it periodically. The same attack applies. This is where we first started thinking about this. The solution there is what we call catastrophic reseeding, which sounds great. It's like a good marketing term. Really, it just means make sure you've got enough entropy before you initialize and before you reseed. Okay, so you make sure that you're not doing this thing where you're putting a little tiny bit of entropy in and then letting more outputs come out, putting a little bit more in and letting more outputs come out, because that just, you don't get any benefit from that. And this maybe seems kind of obvious when you look at it, but quite a few real-world designs were allowing this sort of trickle the entropy in and then lose it attack. So, but the nice thing about this is that because, for the entropy source plus DRBG design, we only initialize once and we only reseed rarely. So we can afford to make this very slow. We can afford to be very conservative in when we initialize and when we reseed, right? I think with the entropy pool designs, that's a little harder to do if you want to keep in the spirit of the design. A bigger issue I have with entropy pools, and this is just me making an editorial comment, but I think entropy pools tend to solve the wrong problem, right? So if we were in a world where we didn't know how to make DRBGs, but we needed information theoretic security, and we had a lot of confidence in our entropy estimation, then I think entropy pools would be a really good solution to our problem, right? But in practice, almost everywhere in crypto, we don't need information theoretic security. We're actually using the RNG to generate like an AES key. And so we're not in the world of information theoretic security where we're doing one-time paths. We already know how to make pretty good DRBGs. And we actually, entropy estimation is a lot harder than, I believe, than making a good DRBG. So I think saying we can make a good DRBG out of AES is not so hard. Saying that we know exactly how much entropy we're getting per sample, that looks hard. So I feel like the entropy pool design actually solves the wrong problem. It's a clever solution to the wrong problem. So that's my kind of my editorial bit. However, I will say for the rest of this discussion, when I'm talking about entropy sources, they actually work okay either for either of these constructions. The entropy sources I'm describing will work with an entropy pool because they do give you a claimed amount of entropy per sample. They'll work either way. However, SP890 in general assumes this sort of, let me get back to my picture, this sort of model, the entropy source plus DRBG model, where your entropy source is really only being used to generate a seed once for your DRBG, and then you update the seed periodically. Okay. So before I go on, do I have any questions about this? Okay. All right. This is the great thing about doing it at 3 in the afternoon is you're all too tired to doze off. Okay, so let's talk about entropy sources. So the first thing you might ask, what is an entropy source? In my conception, the rest of this talk, and what I think of as being useful for an entropy source, it's the place where we put the unpredictability of our system, right? So where we want to say we need to get a certain amount of unpredictable bits for our system. We're going to put that all on the entropy source. The entropy source provides bit strings, right? They have to be bits because we have to be able to use them. And the bit strings come with a guarantee. They come with a label that says how much entropy they have. A guarantee or a promise from the entropy source that says, I'm telling you, you've got at least, say, 10 bits of entropy in this. Maybe I'm giving you a 128-bit string, and I promise you there are at least 10 bits of entropy in this string. That's my conception of an entropy source. It's the one we use in 90B, and I think it's a generally pretty useful one, right? I also will include the idea that it should have some sort of internal testing to make sure that something hasn't died. That's important because the underlying non-deterministic stuff is often quite fragile. You know, the things that you're doing with ring oscillators or thermal noise or something, that can be very fragile, that can change over time, and it's important to have some sort of internal testing to make sure things haven't failed. This document that we're about to publish, 890B, is all about how to build an entropy source. Okay? So the big takeaway, entropy source gives you bit strings, it tells you how much entropy they have, and this is so you don't have to think about the non-deterministic parts anywhere else in your system. Everywhere else you can think of as a deterministic thing, and all the non-deterministic stuff just happens in this one little box. Okay? I think as an engineering matter, that makes life easier if you're not trying to have to think about multiple things. So I've talked about entropy. What do we mean by entropy? When I use it, at least, when I hear kind of casual conversations with cryptographers, entropy kind of has two different meanings. Sometimes people talk about entropy as sort of the property of unpredictability. That the string is entropic, or that there's some entropy in there somewhere. There's something, you're just saying it is an unpredictable thing. It's not entirely deterministic. Other times we mean, by entropy, we specifically mean a particular measure of unpredictability. Right? How do we measure the uncertainty about this value? And in our case, we're going to use something called min entropy. I'll get into why in a second. So there are a bunch of different measures of entropy. Actually, these are only 3. There are a lot. You can spend a lot of time on these. Shannon Entropy is the one that almost everybody learns when you have like an information theory class. Shannon Entropy is actually, it's exactly the measure you want when you're thinking about channel capacity, right? I've got some source, but I can describe it with a probability model. I want to know how many bits I need to send, on average, to send a output from this source, right? That's Shannon entropy. Collision entropy is a different measure. You can see the formula here. I hope I wrote these right there. Did these slides like I think last night or 2 nights ago, so I hope I didn't mess up the horns, but I think, yeah, that looks right. And then min entropy is the base 2 log, minus the base 2 log of the maximum probability in a probability distribution. Okay. So if we're looking at some thing that has multiple probabilities, right? So the probability of P1 that you get a 0, probability of P2 that you get a 1, probability of P3 that you get a 2, whatever. And we want to measure the entropy of it. We can use one of these formulas, and each of these gives us a different number in general for a given probability distribution. Okay. And so we use min entropy in our work, and this is generally used in your thinking of, at least most of crypto, you're talking about min entropy. Well, why do you want to use min entropy? Min entropy tells us how likely an attacker is to guess a value on his first try. So, for example, think about passwords. Everybody uses passwords, right? If you understand how passwords work, typically the attacks on them are, I'm going to try to guess a list of passwords and see if I can make one. If I can find one that you use, find the one that you used, and I can usually check these relatively efficiently. So, with min entropy, what I'm asking is, what is the probability of the most probable password? Which is probably like a password or dog or something, or a blank. So, if you think about the security of somebody's password, you actually probably want to think in terms of min entropy, right? I want to know how likely is it that the attacker is going to guess it on the first try, right? I might actually want to know something more like, if I give him 10 tries, how hard is it for him to guess? But min entropy actually lets us bound that, right? If the first try, you had a probability of 1 in 100 of guessing it, well then we know that with 10 tries it can't be any more than, or it can't be any higher than 10%, than 10 out of 100, right? Also, if we're attacking multiple things, so if you think in the world of passwords, you think of I'm guessing one password on each account or something. You'd also be thinking about min entropy being the interesting issue, the interesting question. So passwords are a place that you might be familiar with. We also want to do this when we're thinking about initializing a random number generator, right? Like the seed for an RNG. So I want to give you an example that kind of illustrates why we wind up with min entropy in particular instead of Shannon entropy. So I want you to imagine a source. We have an entropy source, a source of unpredictability. This source has this funny distribution. Half the time it gives you 160 bits of zeros. The other half of the time it generates a random 160-bit value, everything except the all zero string, with equal probability. So about 2 to the minus 161. So there's one value with very high probability and then all these other values with very low probability. Okay? Imagine using this source to derive the keys. You're going to hash this and use it to derive like an AES key. The question is, how many samples do I want? Because we would like to use the entropy number to tell us how many samples we need to get like a 128-bit key securely. Okay? So if you did this, if you compute the Shannon entropy here, and I tried to go through the calculation, it's if I didn't mess up my math here, it's 81 bits, right? So and that sort of makes sense if you're thinking about channel capacity. If you had this source that half the time sent a 0 and the other half the time sent some random 160-bit number, you can kind of imagine the encoding you'd use so that when it sent a 0, it would be a very short encoding. When it sent anything else, it would be a longer encoding that gave an extra bit. That's, you can see why maybe you would average out to 81 bits per sample. That sort of makes sense. However, that isn't very good for figuring out how hard it is to guess. So min entropy says 1 bit. So if we use Shannon entropy, what we would say is we would need probably like 2 samples, and we'd have more than 128 bits, right? We'd say I'll take 2 samples from this source, and then we'd have enough entropy to feel like we were okay to derive the key, because we'd have 162 bits, right? If you did that, then there's a 1/4 probability that the attacker would guess your key on the first try. Okay, so this is sort of disastrous. If you're using min entropy, you know, we're going to tell you use 128 of these samples, and then the attacker has exactly the probability you would want for a 128-bit key. He has a 2 to the minus 128 probability of guessing the key on the first guess, right? So this is exactly why we use min entropy instead of like Shannon entropy, and that's kind of useful to know because Shannon entropy is probably the thing that everybody's heard of, and it's the thing you study in like an information theory class, and then lots of people want to know, well, why are we not using Shannon entropy? Well, I should say there are relationships between these. So min entropy is a bound. You know, the other thing about this is when you have very close to full entropy, Shannon entropy and min entropy are very, very close, right? So if you're like 0.999 bits Shannon entropy versus min entropy, they're not very far apart. And you can kind of work out why that is with probabilities. So some other advantages of using min entropy that are practical. The big practical advantage, if I'm trying to look at a probability distribution for some noise source, right, all I need to know is the probability of the most probable value, right? I don't have to characterize the entire distribution. Nothing else matters but the most probable value. Okay? So as a practical matter, it's a lot easier to estimate that with small numbers of samples and get a good estimate on the thing that is the most common than trying to get probabilities on all these things that only happen once in every million samples. So collision entropy, Shannon entropy, guessing entropy, those all want the whole distribution to be able to be computed. Min entropy also plays well with this particular framework called Predictor Framework, which we use for entropy estimation. I'm not going to go into a lot of that in this talk, but it plays well with some of the other technology that we like to use. And I find it a very intuitive way of thinking about the problem an attacker faces when trying to guess the input to the DRBG. So, any questions at this point? Okay. I don't know if this means you're a good audience or a really hard one. I can't tell yet. So, hang on just a second. So the next thing I want to talk about is entropy sources in the sort of view of SP 890. Now, SP 890, like I said, is this document we've been working on for a really long time. It's finally coming out here very soon. And it's all about how to build entropy sources. So this is a picture of kind of our schematic drawing. So when we talk about an entropy source, the first thing we do is divide it even further. So before we said the entropy source is the place where we put all the non-deterministic stuff, and everything else is deterministic. Now, even inside the entropy source, we're moving the non-deterministic stuff to this one little place right up here, this noise source, and make everything else deterministic. And of course, that's because we want to make it easy to analyze, right? We want to be able to think about it in terms that are easy to kind of get your head around. So the noise source is where the entropy comes from. So we say an entropy source is something that contains a noise source, but it also is doing this health testing, maybe this conditioning, and it's giving us outputs with a known fixed amount of entropy per output, right? So an entropy source comes with labels on it that says, here are 128 bits and it has 10 bits of entropy, and I've done some testing. And a noise source is just the underlying unpredictable thing. So a noise source might be actually a ring oscillator being sampled on a stable clock, okay? Or a set of flip-flops being set into a metastable state, and then you watch which way they drop, right? In software, I think the usual way that you do software entropy collection is you look at interrupt timings. Okay, so these are all things that have some unpredictability, right? So those are your noise sources. For health tests, the idea is just to make sure that the noise source hasn't died, that it's still working. And conditioning is optional, but it's very commonly done in entropy sources, and it's basically to improve the statistics of the outputs. Maybe you've got your noise sources generating these outputs that are very sparse. Maybe it's thousands of bits of output per bit of entropy, and this is not very practical to use. So maybe you'd like to condense it somehow, process it, and then only output a few bits, only output one bit at a time with a very close to full entropy, right? So the noise source, an important thing to understand is in our kind of scheme, the noise source has to provide bits. right? So we want to talk about deterministic, everything else in the system being deterministic and being able to be things that work on bits. So the noise source is going to provide us some bit strings, right? And that typically means some non-deterministic mechanism, some way of sampling it, probably some digitization unless the thing you're sampling is already inherently digital. And that all together gives you a noise source. And so I gave you some examples before. Users' mouse movements are not used so commonly now. It used to be very common in old cryptographic software. You would have, PGP would have this thing where you would, when you're generating your key, it would ask you to either type on the keyboard or move the mouse around, right? And the goal is just to capture some unpredictable things to say. It would be very hard for an attacker to precisely model the user and his mouse movements, so maybe we can get some very unpredictable things in here. So, but
you're assuming you already have a good measurement of how much entropy the noise source is?
I'm not assuming that we have that yet. I'm going to talk about how we try to get that, although there are some real issues with 90B. The process piece of 90B has some real limitations. And they're imposed on us by the way the FIPS validation labs work. So I'll talk about that later. But the noise source is sort of the heart of the entropy source. So if that stopped working, you'd be gone, right? There would be no useful work being done by the entropy source. And so it's really important to figure out if the entropy source is working correctly, to evaluate it originally, and then also to keep testing it, making sure that it hasn't failed. So that's the next component is the health test. Health tests are trying to find major failures. The thing you have to understand, the health tests, especially that we have this requirement for continuous health testing, they can't consume a lot of resources. So they're pretty limited. They're not going to be able to find subtle flaws because you can't do that if you can't consume any resources, right? The goal is to catch if something goes badly wrong with the entropy source. You can sort of think if you've got some model in your mind of how the entropy source should be behaving. If it fell wildly out of that model, you'd like to know. You'd like that to cause the device to make a little red light come on or something and stop working. So 90B actually defines two health tests that are very generic. Our goal is actually not to get people to use our health test. It's to say you have to use either of these or come up with your own that are better. Because if you know we're doing this very generically, we don't know what your noise source is, so we'd like people who are designing them to do a better job. So the last major component here is conditioning. Conditioning is optional, right? Nobody has to do conditioning. You can design you can find a noise source that produces output bits that have enough entropy, have good enough statistics that you're comfortable just outputting directly. But a lot of noise sources will try, or a lot of entropy sources will include conditioning to try to get up close to full entropy because it's easier to use those bits, right? In particular, if you're generating bits that have 0.99 bits of min entropy per bit, you can just kind of use them for keys and stuff, and you're not taking much of a hit in terms of security. If you've got outputs that have like 1 bit of entropy every 10 bits, then you've got to do some additional thing like hash them before you can get a key out of them. Conditioning is, of course, it's optional, but it's also, it's optional what you do. So some designs have cryptographic conditioning, doing like a hash function or a block cipher. The Intel hardware RNG does AES CBC MAC as its conditioning function. Okay, but you don't have to, it doesn't have to be cryptographic. A very common thing that's done is von Neumann unbiasing. It's, how many of you have heard of von Neumann unbiasing? Okay, like a few. So it's a trick for if you've got a source with an IID distribution. So you've got bits, and you don't know what the bias on the bits is, but you know that they're identically distributed, right? So you just have this trick where you say if you look at pairs of bits, and if they're both the same, you throw them away, and if they're both different, you take the second one. I think that's an easy way to describe it, right? So what you're doing is making sure that you unbias this. If you've got a biased source going in, you get an unbiased source coming out. The thing with von Neumann unbiasing, the reason I bring it up, is because it's used all the time in noise sources, or in entropy sources, and it's usually used incorrectly, right? The critical thing about von Neumann unbiasing is if the source is not, like if the bits are correlated, then you can actually increase the bias. You throw away entropy with it. So it's so maybe if you don't remember much else, remember, don't just throw in von Neumann unbiasing because you vaguely remember it and it's kind of cool looking. And von Neumann was pretty smart. I can't go wrong using something he designed, right? So the next thing I want to talk about is in the 90B world, how we imagine testing the entropy source, trying to figure out how much entropy it has. And I should say, this is all kind of bent around the idea of FIPS 140 validation. FIPS 140 validation says, you are a designer, you design something, your company designs it, you now want to get it validated so you can, FIPS 140 validation is required to sell things to the US government. I think the Canadian government and Japanese government at least do also have programs like this. This is actually, it's done in conjunction with the CSC, with the Canadian government. But there's also the Japanese government does something similar. But with this, you have to do it to sell to the government, but also a lot of private companies want to have validation in the US to accept something. So the trick here is for FIPS validation, this is you produce a product, you go to a lab, one of the independent testing labs, and you ask them to do validation on your product, and you show them some things, you give them some data, and you pay them a bunch of money, and eventually either they fail you or they give you a certificate. And the certificate says what algorithms do you correctly implement, what approved things are you doing, you're following their rules. So you should think of all this in the context of this world where somebody is designing something and submitting it to a lab, and the lab is evaluating it, trying to come up with an entropy estimate. So that maybe makes the rest of this make more sense. So the first step is collecting data. So collecting data in this case, what we require is a sequential data set, which is 1 million successive samples from the noise source. Remember, I'm not saying just the entropy source, which might be processed. I'm saying the noise source. So whatever the actual ring oscillator is, the actual thing where you're sampling from a noisy diode or something, the actual raw bits have to come through and be given to this test. So this is 1 million sequential samples from this. We also do a restart data set. I'm going to talk about the restart testing in a bit, but this requires some sort of power down and power up or hard reset between operations. And each time you generate 1,000 bits. And you just basically construct a matrix. The first row is the first 1,000, then you restart it and get another 1,000, that's the second row, third row, on and on. Okay. Also, in some cases, when you're using a conditioner, you may have to test the outputs of the entropy source, the conditioned outputs. And I'll talk about why and when that happens. So the next step is figuring out IID versus non-IID. So first of all, what does IID mean? Independent identically distributed. All it really means is I've got a sequence of samples and I can think of each one as an independent experiment. I don't need to think about where they are in the sequence or their relation to other things. So I don't think there's a correlation between one bit and the next. I don't think that there's a time series thing going on. Great. And if you have an IID source, right, or an IID distribution, it actually makes your life a lot easier trying to analyze it. So how do we determine if a source is IID? Well, the first thing that happens is the designer has to claim it. So if the designer, when he's submitting this to a lab, says, I believe my source is IID, then it will be evaluated and it will check to see if the tests agree with it. Okay. If they say it's not IID, then we just would never run the test because we'd say you as the designer know your source better than we do. Or better than labs do it. So if they claim it's IID, then we'd run basically a bunch of statistical tests to try to prove that the source is not IID. And we require some justification for the claim that it's IID, right? So it's not just, they just claim that they're supposed to explain why. However, I have to say the FIPS validation labs, we don't think that they're capable of doing a great deal of careful evaluation with the resources they have of these claims. So there's a documented claim that says says here this is an IID source and here's why, but we don't actually think that the labs can do a great job being skeptical about those claims. But if you run the test and if we can't disprove it with these tests and you claim it's IID, then we, or the labs in this case, are going to assume the source is IID for entropy estimation and keep going with that assumption until we find a place that it's wrong. So the IID testing I'm not going to go into a lot of detail about it. We do a couple standard things. We do chi-square tests of independence and goodness of fit. So goodness of fit, we break it into a bunch of pieces. We break the sequence into, I think, 10 different pieces and do chi-square goodness of fit to say that is it the same distribution in different parts of the sequence. We also do this chi-square test of independence just to make sure that we're not seeing serial correlations. The most important thing we do, though, is this series of permutation tests. And what we do is we have this whole set of statistics that we compute on the original data set. And these are things like the longest run, the number of runs, the number of sequences that are in the same direction, going up or going down, a whole bunch of things. And I believe we're up to like 11 or 12 statistics at this point. For each statistic, we compute it on the original data set, and then we do 10,000 shuffles of the data set. So we pseudo-randomly permute the data set, and we compute those same statistics on each of the shuffled versions. And the idea is, if the claim is we are IID. If this source is IID, then every permutation of the input sequence is exactly as likely to have come up as the original sequence. So if we think that this is IID, then shuffling it should in general give us about the same statistics as it had originally. So we shuffle the data set, and then we look to see if the original statistic is in the tails. Is it way far in the tails in either way? If it is, and we can characterize how probable this is to happen on an IID source. If it's in the tails, too far in the tails in either direction, then we will reject the source, or reject the claim that it's IID, right? So if, for example, one of the tests is to run the BZ2 Burroughs-Wheeler compression algorithm on the sequence. So if it turns out that there is some pattern that is easily caught by the compression algorithm, right, so it compresses very well, then what you would see is the original data set would compress really well, it would give you a small output length. All of your shuffled versions would lose that structure, and they would compress very badly. And the result is that you would have the result of the compression would be way in the tails. It would be the original data set would be the smallest value of all of the statistics. So that's the idea we're doing with the shuffling tests. And the goal here is just to try to falsify the claim, try to contradict the claim that it is IID. So if we can't contradict that claim with our statistical tests, then we say, okay, now we're going to evaluate it as though it is IID. So if you think in the AIS 31 world, a claim of IID is more or less a stochastic model, right? Because once you have an IID, so we've just said that we believe that the source is IID, so we think that every sample is an independent event. So now figuring out the maximum probability is just counting and then doing a little confidence interval. Super easy. It's like the first, you give it to somebody who's just taken their first stat class. Okay. On the other hand, the non-IID case is much messier because now we're saying we don't know what the distribution is. All we know is that it's not IID. So we now apply many different entropy estimators. And the idea is that we have these three different categories. One set that was originally designed by some NSA guys it does parameter estimation. So what this does is each of these tests assumes a particular probability model, right? And then says, if this probability model were correct, let's estimate some parameters of it from the data. And then using that, let's figure out what the entropy would be. This is a fairly straightforward, sensible sounding thing to do. The problem is, if your model is a reasonably good fit for the data, you get a reasonable answer. If your model is not a very good fit for the data, you get crazy answers, sometimes wildly above, sometimes wildly below the correct number, right? And we can show this in simulations. So we've done a lot of testing where we simulate entropy sources with various distributions using, where we simulate them in a way where we know what the correct entropy should be. And we can test them, and you can find where these tests give crazy answers because they're making a bunch of inappropriate assumptions, right? So in order to get around that, I did some work. This is something we published a couple of years ago with Meltem Turin and Carrie McKay and I published. We did these things called predictor tests. The idea with a predictor test is you're building a set of models against. You're making up an assumption, a probability model sort of assumption about your source. Each of these models is used to make predictions. So what you do is observe the sequence up until now and predict the next bit, and you just keep doing that for the entire sequence. So the benefit of this, as opposed to the parameter estimation models, is if a predictor test is a bad model, if the model is very inappropriate for the data, then what happens is the predictions are bad, right? Pretty much by definition, if I have a crazy model that shouldn't be a good description for your data, but it predicts your data, it predicts your output super well, then it's a great model, okay? So we can take all of these predictor tests and take the one that is the best, that gives the most accurate predictions, and use that to estimate the entropy. And the fact that most of our predictors were making silly assumptions that don't track well with the data, that doesn't hurt us at all, because they just give really bad answers. They're very bad at predicting, and we have one that's really good at predicting. That's the one that wins. Okay. So
Question, John, can't you do the same thing with the parameter estimation? You can see how good the parameters are estimated.
Yes. You could do something where you first tested to see if the model was an accurate representation, or was a good fit for this data, and only use the estimate if it was a good fit. That's not what these tests were doing. And we actually took a couple of their tests out as a result of this when we looked at this and saw this problem where they were giving crazy numbers. I think a couple of them we only do on binary data because they behave well on binary data, but not on others as well. And so we also do a couple of other tests that are basically very straightforward, sort of counting things. And then the goal here is we take the minimum of all the estimates. So we're trying to make as conservative an estimate of entropy as possible. So we want to take the minimum entropy. That means we want to give it as little credit as possible. We want to, if there's any of these models that say you don't have very much entropy, then we want to go with that and be super conservative. So the process for entropy estimation here is we do this original entropy estimation on the sequence. We also, if the sequence of data is not binary, so if it's like 8-bit bytes or something, then we also break it down into bits and process the binary sequence and do an entropy estimation on that and make sure that doesn't give us a crazy answer. Okay? Because it's just there are some particular patterns that might show up in the binary data that wouldn't show up when we saw these bigger pieces. And so we want to make sure that we check that. And so we get a binary estimate, we get an original estimate, we get an estimate that the submitter gives. The submitter is required to tell us what he thinks he's got in terms of entropy. And he has to justify that. And then we make this h sub I, which is the minimum of all these three, right? So we've got, remember, if we're doing non-IID, then we're taking the minimum of a bunch of these estimators, and then we're taking the minimum of that with all these other things, right? So we're trying to edge toward the lowest number that makes sense with the data. So the next part that I want to talk about is restart testing. So first of all, the big picture. What's the deal with restarts? We've got all these tests where we take some source, we generate a long sequence of outputs, and we do some sort of analysis of it to try to figure out how much entropy it has. However, when you just look at one sequence, there are a lot of patterns you might not see. For example, maybe right after you start things up, for the first 50 or 60 bits, you have some bias that then disappears as the device runs longer. Okay? Or alternatively, maybe you've got some sort of thing going on where the early bits, where some bits, maybe you have something where once every 1,000 or once every 20 restarts, you get some weird pattern. You get a big long string of zeros at the beginning or something. Those would all be interesting things to see. Maybe the 17th bit you draw out of the sequence every single time is always a 1. That would be interesting to know, right? All these would be things you would never see if you just looked at a single sequence. So we wanted to look at restarting the noise source many times. And part of the goal here, we explicitly say, it is allowed for the designers to say, we start up the noise source and we inhibit output for a certain time until we think it's ready. We explicitly want them to do that. The point of the restart test is largely to make them actually do that by saying, if you don't do this and get it right, then we will reject your source. Okay? So, really the idea here is we want to make this assumption that a good source should be about the same across all of the restarts and have about the same entropy per sample at every position. So we don't require the non-IID sources, obviously we don't require them to be IID, but we do want to say that we don't have times where we're getting 5 bits of entropy per sample and times where we're getting 0 bits of entropy per sample, because then you couldn't use the outputs of this in an entropy source and safely generate keys or generate seeds for a DRBG. So the restart data set, you basically do a hard reset or a restart of the device, you generate 1,000 successive bits, or successive samples, they may be bigger than 1 bit. And then you restart it again and do another 1,000, and you build up a matrix of 1,000 by 1,000 samples. And when you think about this, each row is the result of the beginning 1,000 samples of one restart, and each column is the kth sample from each of these restarts. So the first column is the first value you got out every single time. That's probably an interesting thing to look at, that first column, because if there's a weird pattern where you always get a 0 at the very beginning, that'd be where you'd see it. So we then construct 2 additional data sets. The row data set, we just take each row, each restart, the first 1,000, and we concatenate them together. So now we've got something where if there's some pattern that recurs in the first 1,000 bits every time, or a lot of the times, then we're going to be able to see this in this new sequence. We also do something with the column data set. We concatenate the columns, so column 1 and then column 2 and column 3, turn that into a sequence as well. And so we're kind of unraveling the matrix 2 different ways. And when we do the column data set, we're now seeing all the first samples, then all the second samples, then all the third samples. So again, there are a lot of patterns that you might not see in the ordinary data set that you would see really clearly in this kind of varied data set. For example, if you had something where where the first 2 or 3 samples had a very different distribution than all the others, this column data set will have a really interesting pattern. The beginning will look very different than the end. So the first thing we do from this, before we even do any more of things with the row and column data sets, is we do this sort of sanity check with the binomial distribution. So we can just say, if we think that we know the entropy estimate of this source, right? So we're going to estimate P max, the maximum probability of any sample. That is immediately defined from the entropy. Remember, min entropy is just the base 2 log of the maximum probability. So we can always go between these. So we can say from this min entropy estimate, I'm going to say here's my maximum probability. And then from that, it's easy to say, I can put an upper bound on how many times I should see any sample appear, given this maximum probability. In 1,000 samples, which is 1 row or 1 column. And then I'm going to do a binomial test on each column and each row. And I'm of course going to set the p-value correctly so that I'm doing 2,000 tests, so I've got to set the p-value to be pretty small so I don't have a high false positive rate here. But that's easy to do. And so the result is, if I get more than this very permissive upper bound, then I'm going to reject the source entirely. That basically is where I say, something about the restart behavior of this source is so weird that we no longer believe we can evaluate it with our tools, right? Our existing test search is not the right tool for this. We no longer feel like we can give a good model for this. So we now have the row and column data sets. And what we do with those is we just apply the same entropy estimates. We apply the entropy estimates from before, but now on the row and column data sets. So what that tells you is, if we have some pattern in the row data set, so the very first samples always look a certain way, or we get a repeating pattern that often recurs, maybe once in a while you get the same outputs from a restart right at the very beginning, then we will see this in the row data set. The row data set will be highly patterned and it will show up in our test. Our test will reject it. Similarly, with the column data set, if there are a lot of bad things that can happen, and that with respect to this restart behavior, and they'll show up. They will create a statistical artifact here that will be caught by our tests. We actually did a fair bit of simulations of various kinds of failures in restart behavior, and verified that these would actually catch a lot of bad behavior. So anyway, when we've done this, what we're going to get, we're going to end up with a row data set estimate and a column data set estimate. So we've just now got entropy estimates. We have the original one from the sequence, maybe one from the binary. Now we've also got one from the row data set and the column data set. And if these are wildly different, that's interesting, right? So if the row or column estimate is less than half of the other estimate, then we reject the source entirely. Just throw it away. Half is an arbitrary line. It's not exactly clear that it's the right place, but we could not find a better place to put it than we could be confident in, right? Otherwise, what we do is we take the minimum. So if the row data set gives you 80% of the entropy estimate of the original sequential data set, then we just lower your entropy estimate, right? But if it's too low, then we say we're no longer confident that our model is a good description of reality, so we just have to throw it out. So the big picture here is we're doing this original entropy estimate from the sequential database, we're getting the submitter, we're doing the binary estimate, we're doing the row and column, and then we're taking the minimum of everything to try to give us very conservative, minimal entropy estimate. So that all sounds reasonable, right? And we can fail, right? So what's the problem? Okay, so the big problem here, right, is we know we're living in a state of sin, right? Well, that's John von Neumann's quote about deterministic. So we're not doing deterministic random number generation. We're still living in a state of sin, right? Because the right way to do the entropy estimation for a noise source is to actually do statistics, to really understand the source. Build a model of it, analyze it, and then base your build a probability model based on that, and then do entropy estimation. Unfortunately, we can and we do tell people that they should do this in the standard, but the FIPS labs are going to be evaluating these things. We don't believe they have either the expertise or the resources to actually do a good job evaluating these things. So the submitter is supposed to document his probability model, but we don't have a lot of faith that the testing labs are going to do a great job of pushing back on these claims or analyzing these really carefully. So what we're able to do, given the constraints we have within the FIPS 140 process, is we require the design documentation, we require them to justify their entropy estimate, but then we have this sort of set of tests to try to catch the bottom, try to say, let's make sure that we at least catch as much as we can of really screwy things. But the right way to do this is to take this set of tests of entropy that we have and use them as a sanity check on your model. Right? So ideally, you should be doing statistical tests on the outputs at the end after you've done this modeling, and then you should say, oh, wait, these tests are showing a lower entropy than my model says, I've got a problem. Right? What we can do is just say, here, we're going to award you an estimate based on what we know. Right? So the next thing I'm going to talk about, and this is one of the components we talked about before, when we're done, once we've evaluated, I've been talking about how you basically validate a noise source, right? So you get an entropy estimate from it, and you maybe throw the noise source away if it's really bad. But the next thing I want to talk about is health testing. So remember, here we are, we just talked about the noise source and how we validate this. Now we're going to talk about the requirements for health testing, okay? The goal with health testing is, really the intuition, when you come down to it, is non-deterministic stuff is fragile. It's easy for it to go wrong and hard to verify it as an engineering matter that it's working correctly or that it's going to stay working correctly, right? So we would like our noise sources to have some health tests going on to make sure that they haven't failed catastrophically, right? The health tests examine the raw noise sources. So we're not looking at the conditioned outputs where there's been some processing and maybe the badness is masked. We're hopefully seeing the raw bits coming out. So we have some hope of finding problems. The issue here, in general, we're talking, the main thing that we're talking about right now is continuous tests, things that have to run all the time. So they have to have a really minimal performance impact, right? And so you have to make sure that the memory and the computation load per sample is quite low. There's also this category of startup tests and this category of on-demand tests. I'll talk a little bit about those, but not a whole lot. I'm really mainly talking about the continuous tests here. 90B has 2 recommended health tests, right? So we have 2 tests that we've defined. I'll talk about them. First thing to understand, it's really important with these tests to do to have a very low false positive rate because these tests are running continuously. Okay, so you might have a hardware RNG that might generate 1 million bits a day. So obviously, like if you have a false positive rate of 1 in a million, well then once a day your entropy source dies and you have to restart it, right? You don't want that. So you have to tune the false positive rate to make sure the expected number of failures is low if the source is behaving well. But this is a trade-off, right? It's a trade-off. It's standard trade-off everywhere in statistics, right? You can make the false positive rate lower, but then you also miss more. You miss more bad things, right? So we think in general for the tests that we've looked at, 2 to the 40, 2 to the minus 40 or 2 to the minus 50 false positive rates are things that are not so hard to achieve and get reasonable numbers. So I'm talking mostly about continuous tests, which are going on all the time behind the scenes. No resources, no buffering. So these tests are being done constantly and the bits are being put out, and eventually maybe they'll detect an error. We also have this notion of startup tests. The idea is that for the startup test, this ties into FIPS 140's requirements that says that the module should have startup tests. Most of the startup tests we do in FIPS 140 are, I'm sorry, but they're kind of goofy. It's a relic of an older time. We do things where we make sure that AES is still correctly encrypting by doing one test encryption of AES. So not so useful for most things. However, actually doing some startup tests on the noise source seems like a very good use of resources because the noise source seems like something that's a lot more likely to die silently than the AES engine. So you do this, in the case of the startup test, you run it on a sequence of noise source samples before those samples may be used for anything. You can buffer them and use them after they've passed the test, or you can just throw them away. We also have on-demand tests, which can run when requested, and those, it's okay if those are just a rerun of the startup tests, right? The vendor is allowed to provide more tests, but doesn't have to.
And can I also from the previous slide?
Oh yes.
The minus 42 to the minus 50.
Yeah.
Apply it to which of those?
Oh, this would be to the per sample. This would be the per sample. So you've got some test that is looking at each sample, and you might want to bound it to say it won't have a false positive rate higher than 2 to the minus 50 per sample it examines. Okay. So, although in general, these tests have to have a little bit of state, so it's, you know, you're doing an average over large numbers of sequences. Right. So if you think of 2 to the minus 50, and then if you think if you were doing 1 billion bits per day of output, which seems very high, then one day in every million roughly you would fail.
That's how you came up with the number.
Yeah, this was from basically responding to comments from previous drafts. You know, we got comments from some designers, some hardware designers who had concerns because I think before we were talking 2 to the minus 40 as just a default number, and some people said, well, that's too high. Yeah.
And you mentioned that there's no buffering required. So is that possible that when you detect the failure, the random numbers has already been used?
Yes. Yes. The idea of the continuous tests, these tests are really just going to catch the really gross failures. So if the thing fails like in the middle of use, now we have a startup test where they're being buffered, but for the gross failures, they would, you know, we hope that it will catch them relatively soon after the failure happens, but it is possible that these outputs have already been used. And that's the trade-off is if we don't do that, then we require buffering large numbers of values, right? And then it imposes a fairly high cost on the device. So let me see. So these are the 2 health tests we defined. And these are the repetition count test, which is just an update. FIPS 140 now has this thing called the stuck test, which is applied in a really stupid way. It says the output of your DRBG, your algorithm, they make you store the previous one and check to make sure that the DRBG is not stuck, right? So the cryptographic algorithm. So this is goofy, right? It essentially can't happen that this would get stuck, right? But it makes sense to look at the noise source and make sure it hasn't gotten stuck on a value, because some noise sources can't. So a repetition count, we're basically going to look at the source and see when we've seen the same value too many times and it's gotten stuck. The adaptive proportion test, we're just going to try to detect when one value becomes too common relative to the claimed entropy sources, or claimed entropy level. These 2 tests do not require a lot of resources. They don't require buffering. You can use the outputs as they're produced, and they allow widely tunable false positive rates in a pretty straightforward way. The only thing we need to know is the entropy per sample, right? And that's important because these are generic health tests that we're saying you can use these if you don't have your own that are better. And so we can't make any assumptions about the source for these two tests except that they know the entropy per sample, because we already know they've got that from the previous steps in validation. So the repetition count test, really all we're doing, this is a really straightforward thing, is we're saying, what's the claimed entropy per sample? Well, we can use that to derive P max, the maximum probability. And then we can, if we know the maximum probability of any sample, we can say how many times that sample should ever recur, right? So we say, there's never a time, if we claim that each output has 1 bit of entropy, that means that there is no, every output, there is no value that has a higher probability of occurring than 1/2. So we know that the same value shouldn't recur more than a certain number of times. And you can compute this. You can compute the probability. So given the false positive probability, we just do this very simple calculation, and we get a cutoff value. And if we basically have we have two registers. You effectively need two kind of registers here if you think about it that way. You keep track of the previous value that you've seen from the noise source, and a counter that says how many repetitions have I seen so far. When the next value that comes out is different from the previous value, you zero the counter. And then you move the new value into the previous value. When it's the same as the previous value, you increment the counter. And if your counter ever goes above C, or gets up equal to C, then you signal an error. Okay. So all this is doing is updating the stock test to make sense. Right? So if you have a source that has a lot of entropy, if it has 8 bits of entropy, then you should never see like 5 samples in a row that are the same. If you have a source that has 1 bit of entropy, then you could have a lot more samples. It'd be okay. If you saw 8 samples that were the same, it wouldn't be a surprising thing. That should happen like 2 to the minus 7. You should have probably like 2 to the minus 7 or something. So you have to choose this cutoff value based on not only the false positive rate, but also the claimed entropy. The adaptive proportion test is a little more complicated, but it's still a fairly simple idea. We have what we call a window size. Remember, we're not doing any buffering, so we're just keeping count. So what we're doing is, we've decided that we're now at the beginning of a window. We look at the next noise source sample, we store it, and then for the next, let's say we're doing a 1024-bit window, that for the next 1023 samples, what we do is we just compare them with this first sample in the window, and we increment a counter if they're the same. Okay? So what we're doing is we're just gonna get a count of how many samples in the rest of the window were the same as the first sample. The goal here is to catch the situation where one sample value has become more common than it should. And the way we do this is, kind of intuitively, the most common sample is the thing that's the most likely to be at every position, including the first one in the window, right? So if a value has become very common, then we hope that sooner or later it will be the first value in the window, and then we will count that value, and then we will detect that this thing has become too common, right? So this is the main benefit of this test is it detects a very easily defined error condition, and and we can compute the cutoff value. In this case, we have to do an inverse binomial computation. So there's not a nice formula. You do it numerically. And then every W sample, so every 1024 samples or something, you reset the counter, reset the window counter, and start over. And the main idea here is you only need these 3 registers effectively to compute this continuous test. So, a question? Oh, okay. So, I should be really clear. We created these tests because a lot of the time when you're working on standards, what you're doing is trying to set a minimum, a floor. Okay? Any competent designer of a hardware entropy source should know their own source. They should know their failure modes. They should know their, what can go wrong a lot better than we do, right? We're writing a standard that should apply to everything. So we've given them these tests, but what we really want is for designers to come up with their own health tests that catch the same problems and more problems, and they're tuned to their source. So we have a mechanism in the standard so that the designer, they can submit their own tests, and basically, based on their own understanding of the source and their own understanding of likely failure modes. And what they do in that case, I think the requirements here, what we do is they need to show that their tests accomplish the same broad goals as ours. So if the noise source starts repeating, gets stuck in a long repeating pattern, or if the noise source, if some value becomes way too likely, then their test should show this. And they can show it by a proof or kind of a convincing argument in the documentation. They can also just do a statistical simulation to show that, because their health tests are something that's algorithmic, you could just do an algorithm and show that this would work if you inserted this failure condition. So the last piece here is the startup testing. Startup testing happens when the module starts up, right? That's what it says on the tin. So the idea here is we require 1,024 samples to either be buffered, or you can just generate them and throw them away if you don't want to have a buffer. Because sometimes you've got a hardware source that doesn't have any ability to buffer anything. So in that case, you can just throw the bits away. But you can't use them, right, until the testing is complete. And the idea is this is when you power up, you run these tests before you start using the thing and try to find out if the source has failed, right? And once again, the minimum requirement is you run your continuous test for 1,024 samples. We want the designers to do more than this. This is the minimum requirement. This is the floor. Hopefully, as designers who know what they're doing, will do more here. But this is more than they're doing now with a lot of the designs, and this is a minimum bar. So, do you have any questions about the health testing? Okay, so maybe it's not the most exciting topic ever, but yeah.
Shannon, why these two tests? Did they show up as generic tests, but we chose these two?
Well, we chose these two generic tests. Number one, the stuck test was already an existing idea, and it seemed like a very straightforward one. The adaptive proportion test was just because we wanted to have at least one other test to catch this condition of the probability becoming higher than it should. And it was the one that we could easily figure out, and it doesn't cost very much. Like I said, I'm really hoping that most submitters do something better that's based on their own understanding of their design. But I suspect that there will be at least some submitters who do the minimum required, and in that case, where they previously were doing the minimum required, which was testing the outputs of the DRBG for being stuck that didn't make any sense, now at least they'll be testing something that makes some sense. But yeah, there probably are other tests we could have done, maybe they would have been better. These are the ones we chose just because they seem to fit the requirements. And so the next thing I'm going to talk about is the conditioning function, and particularly this sort of issue of entropy accounting. So you kind of got this problem here where you've got a noise source, you know how much entropy is going in, you know something about the conditioning function, and you want to figure out some sort of a reasonable estimate of how much entropy is coming out of that conditioner. So, of course, conditioning is optional, right? And generally the goal is to improve the statistics of the outputs, and in particular, to improve the entropy per sample, the entropy per bit, or entropy per sample. So typically what you want to do with the conditioning function is you want to start out with some source that maybe is giving you long strings of zeros and long strings of ones, and it has a little bit of entropy in it, and you want to turn it into an output that's useful. So maybe it's 99% entropy, so it's like 0.99 bits of entropy per output bit or something. So that you could use it for keys or something. You wouldn't be completely shooting yourself in the foot security-wise. So some conditioners actually can allow the source to produce full entropy outputs. That's kind of an important idea. So this is the big picture. This is the big problem, is figuring out this H out. So we've got n bits of output, n bits of input, n outputs of output, q bits, and q, I'll talk about that, that's the internal width of the function. We've got this amount of entropy coming in, and we want to figure out what H out is. We want to figure out what the output is. And I just now noticed when I copied this picture in, I left out the H out, which should be on that bottom arrow. But you know that there is an H out there. That's the entropy coming out. So we're going to get n bits of output out, and we want to know how many bits of entropy we can claim on that, right? So just before we start, we can immediately say some things, right? The answer can't be any bigger than n out, right? Can't be any bigger than n in, because no more entropy can come out of this than comes in. The conditioning function is completely deterministic. No more entropy can ever come out of it than goes in. We can only lose, right? Now, I mean, we could have n in be like 1024 bits and n out be 1 bit, you know, and so we could improve the density, how much entropy per bit we have, but we'll never cause more entropy to come out of this function than goes in, right? That's just a property of it being deterministic. And you can also see, you know, so you can kind of see the parameters of what you're doing here, the limits. So, in fact, why do I say we always have to lose? We can't ever win. In fact, sometimes we have to win, we expect to lose some. Suppose we had a function over n bits. We feed it 2 to the n different inputs. So every possible input we feed in, and we get the outputs, right? Well, we expect if we've got a function that's just assigning things randomly, right? We expect to lose some entropy. We're going to have some pairs of inputs that map to the same output, and some outputs that can't ever occur, right? Because no input ever happens to map to them, right? So this idea of internal collisions, this has a big impact on how we do entropy accounting. We're trying to think about, you know, we've got a 32-bit conditioning function, 32-bit wide conditioning function, and we've got 45 bits of entropy, and it's coming in 70 bits of input, and we've got, you know, how much do we get out? We have to think in terms of how many internal collisions we're getting. So the other thing I have to think about is the internal width of the function. That's what we call Q in this. So the reason we have to think about internal width of the function is because there are some functions that have a narrow pipe in the middle. Okay? So let's say we've got 1024 bits of input, and the first thing we do in this, the first half of the algorithm maps that to 128 bits. And then the second thing takes that 128 bits and expands it back out to 1024. Okay? There are cryptographic functions like that. The sponge functions, the shakes, Ketchak, do exactly this. So it's a bigger internal state, and they do that, and it's good. I mean, they're doing it. It's on the label. It's not doing anything bad. But you can have a function which has a big input, a big output, but a narrow middle, right? And this is exactly that. This can mess up your calculations, right? So you don't just want to think about the output size and the input size, because if you ignored this internal width, you would actually get the wrong answer. You would imagine yourself to have more entropy coming through than you would expect. So the idea of the internal collisions that I was talking about in that previous slide, thinking about happening on an n-bit wide function, it actually, in this case, the internal collisions would happen in this 128-bit value, right? And then come out. And once again, it's obvious, however much unpredictability there is in this input, no more than 128 bits will ever be able to make it through this function, right? It goes through this narrow pipe and it gets squeezed out. So, again, I just covered that slide. So we made a big change for those of you who came to the conference last year. We made a big change in 90B. We had an entropy accounting formula that was conservative, but it was very imprecise and a big discontinuity, and it was very seat of the pants. We just derived it, empirically. There are some ways you can try to estimate the entropy of a conditioning function, but they often don't work for small input sizes, and we care about those. So what we did instead is we have a smooth function that has some theoretical basis, and I'll talk about the theoretical basis and why we do it. And also in simulation, we get very good agreement between the actual results we get and the results we know we should get. Okay? So a lot of the stuff we've done here is built on doing a lot of simulation, where we simulate a noise source, and then we simulate a conditioner, or simulate a noise source and run the tests, and try to figure out from the simulation, are we getting results that agree with reality? So this is the beautiful formula. It looks a little gnarly, but it's actually not. It's actually quite nice. And I'll explain this. This is the formula we're using now for output entropy. So you consider the input, the bits of min entropy input, the input size of the function, the internal width, the output size, and you put these all into this formula, and you get back an estimate for H out. And this is really, this is assuming the conditioner works as well as it can, assuming the conditioner is random, what output entropy do we expect out of this? That's the answer. That's the answer we're trying to compute. So to do this formula, we needed to make some simplifying assumptions. There's no way to get around making some simplifying assumptions if you want to do this, solve this problem for practical sizes. So given the min entropy, h sub n, what we're going to do is we're going to assume what's called a near uniform distribution. Near uniform distribution means there is one high probability value and everything else is low. So exactly like the example I gave you before with Shannon Entropy, right? There's one high probability value and everything else is equal. It's very low probability. By doing this, we get some nice mathematical properties in it, and it makes things work nicely. We also have the idea that the assumption the conditioner maps inputs to outputs randomly. So we're assuming the conditioner is okay. It's not somehow mapping everything to the same value. If it does that, then we'll have a disaster. And we have a way of trying to check for that. So now, when we're trying to think of the min entropy of the output, so we want to know, we know these input distribution, we know the input distribution, at least we know something about it, we know the min entropy. We want to know what the probability is of the most probable output, right? So we've got one high probability input going in. We have lots and lots of low probability inputs going in. And they're all going to get randomly sorted into different outputs, right? Each one's going to be independently going to choose a different output. And we want to know what's the probability at the end of the most probable output. It sounds kind of hard to think of this way. So there's this nice analogy. So if you ever think about probability theory, you probably thought about tossing balls into bins. So imagine we have a huge number of little lightweight balls, little ping pong balls, and we've got one bowling ball. And we've got a bunch of random bins. We're going to toss them randomly into these bins. Okay? And what we want to know is when we're done, which bin is the heaviest. Okay? You can visualize this. So how would we come up with an answer? Well, really, there are two bins that are in contention, right? Either it's going to be the bin that gets the bowling ball, or it's going to be the bin that has the most ping pong balls landed in, right? One of those two has to be the winner, right? Everything else has got to be lighter. And really the question is, does the large number of does the weight of all those ping pong balls that landed in the bin that got the most of them, is that heavier than the difference between the average number of balls that probably landed in that bin that also got the bowling ball, and then the weight of the bowling ball, right? So we're kind of translating this. We want to think about effectively the probability of this output bin that gets most of the balls in it, or that gets the largest number of light balls in it. That's what we call in our formula omega. And then the one that gets the bowling ball, we assume that that has the weight of an average number of light balls plus the weight of the bowling ball. And that gives us our formula for psi. And we've got this nice bound that comes from this paper from Robin Sneager from 1998 that is, actually there are several bounds on tossing balls into bins and which one gets the most balls, how many balls land in the bin with the most balls. This is the sort of problem that people have been thinking about for a long time, so there's a lot of literature on it. And they actually gave several different asymptotic formulas. So we looked at them, tried to find the one of their asymptotic formulas that was closest to the numbers that mattered for our situation, and then we did a lot of simulation and testing to verify that these actually gave reasonable numbers because the formulas were derived asymptotically. So you never know without checking if you have a formula that is true asymptotically whether it's going to be true for the range of values you care about. So you've seen this idea, so here we go. So here's psi, right? Here's the one with the bowling ball in it. Here's the one with all the ping pong balls in it. And what we're going to do is we're just going to find the two probabilities. Those are the two probabilities that matter. One of those two has got to be the maximum. So we choose the maximum of those two. And then we take minus the base 2 log of that. That's the maximum probability of an output. That gives you min entropy. Okay? So this all gives you a nice derivation of this. It's kind of easy to get an intuition for why this should work. Like I said, we spent a lot of time simulating this to make sure we weren't walking off a cliff with it. So what we did with checking the assumptions, because we did assume like the near uniform distribution, we ran a lot of simulations with obviously small cases because you can't enumerate when you've got 120-bit outputs. I mean, You have to convert the solar system to computing resources first. So we did a lot of simulation of small cases with many different distributions where we're, for example, taking a Markov, third order Markov distribution with 2 bits of entropy per sample and generating 8 samples at a time and putting them through our conditioning function. And verified that we consistently got very good agreement between our predictions and the actual numbers that we could measure. So our belief is with good cryptographic conditioning functions, this formula describes reality very well. Now, obviously, it doesn't describe reality very well if your conditioner is like the identity function or something, or it's the zero function, right? But if the conditioner is good, this gives us a sort of an expectation of how much entropy we should be able to get out from the output. So when you're designing this thing, how do you choose a conditioning function? Well, designers are allowed to choose their own. They could screw it up. So if they choose their own, we do some additional assessment. We also specify 6 vetted conditioning functions that are cryptographic. Cryptographic functions are, theoretically, they're not the best tool for this job. The best tool for this job, in some sense, would be universal hashes, or things like near universal hashes. But these are things that have nice cryptographic properties, they're well understood, they're large, we can say that we believe that they're going to behave randomly, so they fit well with our model. And they're things that people are currently using extensively for doing, effectively extracting entropy. Although in this case, we're not necessarily building these are not necessarily, a conditioning function is not necessarily the same thing as an extractor, because here we might just be trying to improve the statistics, not try to get it to uniform ideal outputs. So the vetted functions here that we have right now, HMAC, CMAC using AES, CDCMAC using AES, any proved hash function, and 2 of these derivation functions that are based on either a hash or a block cipher that are defined in IDA. Okay, these are all at least 128 bits wide. They're cryptographically strong. We specify what the internal width is because of course we know the internal width because we can look at them. So these are all the vetted functions. So if you're designing one of these and you want to use one of these, then it's a slightly easier process to evaluate your entropy. So vetted conditioning functions, you don't have to test the outputs. There's no point running statistical tests on a bunch of outputs of like SHA-256, right? It'll just waste your time. We know the internal width, and we allow the formula. The formula is allowed to award full entropy. This formula will sometimes award full entropy when you compute it. The non-vetted conditioning functions, the designer is allowed to choose anything he wants, and then we also test the conditioned outputs. So that's the case when I talked about before where you need to get outputs from the actual entropy source, the conditioned outputs, and test them as well. We do an entropy estimate on the conditioned outputs. It estimates how many bits of entropy there are per bit of output from the conditioned outputs. And we do that so that we can basically check to make sure that the conditioner that they chose their own, doesn't have some sort of pathological behavior that just throws away all the entropy, right? A classic example of a bad conditioning function is, imagine you have some source that has, it's doing a counter, right? So all the entropy is in low bits, and then you just XOR the samples together, right? All your entropy just falls in the same bits, and you throw away most of your entropy. That's an example of a conditioner that would be bad. And so if you did that, it would show up as bad in this sort of testing. The entropy estimate would be bad. Now, of course, you have to say, there are a huge number of conditioning functions that would look okay with this, but would still be bad, because you can't ever write tests that catch everything bad. But at least really pathological cases, we would expect to be caught by this. So the non-vetted conditioning functions, you basically take the minimum of the output entropy that came out of our formula. This little thing here, this 0.999n, is to make a limit to say you're not allowed to claim full entropy on non-vetted conditioning functions. That's sort of a policy thing. And maybe it's right, maybe it's wrong, but this is what we decided. And then this thing right here, this is where we apply the result of the entropy estimate per bit on the conditioned outputs. So if we estimate that you're only getting half a bit of entropy per bit of output, then you'll never be able to claim more than that, right? So the idea is we're testing your outputs, the conditioned outputs, and then we'll reduce your estimated entropy based on whether or not if this test says that it's less than what our formula says. So there are a bunch of properties in the new formulas. They basically amount to, we never think that you can get more entropy in than you get entropy out, and it can't be any more entropy than any of the width of the pipe at any point. So that's really all I have for today. I've talked about different strategies for random number generation in a big picture sense. Talked about entropy and entropy sources. And I've talked a whole lot about how 90B deals with entropy sources. So I hope this is useful to you, and I'd love to hear any questions. Thanks a lot.